The bedrock New York City is bolted to lifts 35 centimeters, 14 inches, a whole floor of a building, straight up, then drops back down. Twice a day under 8 million people who feel nothing. Not the ocean, the rock. You feel nothing because the ground, your building, and you all rise together, like ants riding a trampoline that swells under them. But it's real, it's measurable, and for most of history, nothing on Earth was steady enough to catch it. Here's what almost everyone gets wrong about the moon. You learned it pulls the oceans into tides, water sloshing up a beach. True, but tiny compared to the full story. That same pull grabs the solid continents too. Rock isn't rigid. Over the size of a planet, it flexes like warm toffee. As the Earth spins, every city rolls through the moon's grip, and the crust beneath it bulges toward the moon, then relaxes. These are solid Earth tides, and they move land masses tens of centimeters up and down while you eat lunch. So why did nobody notice for thousands of years? Because to see a foot of motion that lifts everything at once, you need a ruler that measures something the moon can't move in step with the ground. You need to measure time itself. Enter the strangest tool in physics, the optical lattice clock. Forget ticking hands. This clock counts the vibration of a strontium atom, an atom trapped in a web of laser light, humming hundreds of trillions of times a second, always at the same rate. The best one, built at Gila in Colorado, is accurate to 8 parts in 10 billion billion. Run it since the Big Bang, roughly 15 billion years ago, and it wouldn't have gained or lost a single second. And that clock has a secret talent nobody wanted and everybody now needs. Because Einstein was right about something deeply weird. Gravity slows down time. The stronger the gravity where you stand, the slower your clock runs compared to someone higher up. Not a metaphor, a physical fact. Your head ages a hair faster than your feet because it sits farther from the Earth's core, where gravity is a whisker weaker. For a century, that was a beautiful idea you could never see. Then the clocks got good enough to see it in a stairwell. 2020, Tokyo. Physicists hauled 2 of these clocks to the Skytree Tower and split them 450 meters apart in height. One low, one high. The higher clock, feeling weaker gravity, ticked faster. By how much? About 4 billionths of a second per day. They measured the frequency gap between the two. 21.18 hertz, and it matched Einstein's prediction to 18 digits. 2 identical clocks in the same building disagreed about the flow of time, because one was farther from the ground. That precision means a clock is now a gravity sensor. Lift one of these clocks by a single centimeter, and it registers the change. It has become an altimeter that measures height by tasting the strength of gravity. Stack those 2 facts, and you get the punchline the research is built on. The moon deforms the crust. Deforming the crust changes how far you sit from Earth's mass, which changes the local gravity, which changes how fast time runs at that spot. So the moon isn't just lifting the ground under New York. It's speeding up and slowing down the ticking of every clock sensitive enough to notice. What used to be pure astronomy became a line item in an engineer's spreadsheet. A 2026 study modeled the frequency shift the moon's pull alone puts on these clocks, and it lands at the level of 10 to the minus 18, the precision today's best clocks already run at, which means physicists can't wave it away. To keep the world's clocks agreed on what time it is, someone now has to do the once absurd calculation: subtract the moon. And this isn't a lab curiosity. It's the plumbing under modern life. There's a single master heartbeat called International Atomic Time, stitched together by an agency in France from a weighted average of more than 450 atomic clocks scattered across the planet. That heartbeat sets the timestamps on GPS, on stock trades executing in millionths of a second, on the power grid, on the internet's backbone. To keep those 450 clocks honest, engineers already correct for gravity differences down to about a centimeter of height between them. Because a clock a centimeter higher runs faster, and if you ignore it, the clocks drift apart and the timestamps stop matching. The crust flexing under the moon is now part of that bookkeeping, and the stakes are about to climb. Metrologists, the people who define units, are preparing to redefine the second itself, the base unit all of science measures against, using these optical clocks aimed at around 2030. A second has to mean the same thing in Tokyo, in Colorado, in Paris. But if the ground under each clock is rising and falling by different amounts as the moon passes overhead, each clock's tick drifts unless you fold in the tides. The moon has quietly become a variable in the definition of time. Then the story leaves Earth entirely. Because if gravity sets the speed of time, go somewhere with less gravity and time runs faster. The moon's surface gravity is about a sixth of Earth's. So a clock up there gains roughly 56 microseconds every day over a clock down here. 56 millionths of a second sounds like nothing. It isn't. NASA's Artemis astronauts will navigate the moon the way you navigate a city, with signals timed to the microsecond. Let that 56 microsecond drift run uncorrected, and a spacecraft's sense of its own position slips about 16 meters a day. Inside a month, nearly 500 meters, the difference between landing on the pad and landing in a crater. Earth time does not work on the moon. So, on April 2, 2024, the White House sent NASA a formal order: build a new time standard for the moon called Coordinated Lunar Time by the end of 2026. A separate clock for a separate world, because the flow of time there is measurably different. Which brings us back to the ground under your feet, rising a foot and settling twice a day to a rhythm you'll never feel. For all of human history, the moon was pulling on the rock beneath every city, and no one could prove it. We finally built a clock steady enough to catch the moon red-handed, and the first thing it showed us was that time itself bends to whatever's tugging on the ground, even a rock 250,000 miles away.